Welcome, guys. We're on week 11, and two lessons we're looking at are lesson 106 and 107. So, lesson 106, we're reviewing the effects of scaling on volume. And we talked about scale factors in relation to perimeter area, surface areas, and volume as well. So if we consider the effects of scaling on perimeter area and surface area and volume, the shape of the figure does not affect the relationship. Mabel collects marbles. Her marble jar is full. So to make room, she finds another jar with twice the height and diameter of the first. She figures that when she transfers the marbles, the new jar will be half full. Yet she is surprised to find it's only 1/8 full. Recall that the volume of a scaled object does not increase proportionally to the changes in edge lengths. And again, all that to be said, this is the most important aspect that we've talked about. And again, I've let you copy this down on your reference sheet. If you haven't, I highly recommend you do it, because there's a lot of problems where, there's a bunch of different numbers and you don't even really need to calculate all the different volumes and things like that if you remember this relationship. So if we're looking at lengths or something one-dimensional like perimeter, let's say we double the perimeter, or we have a scale factor of 2, and the perimeter is going to be 2 times that of the original. And if it's area, that's area, lateral surface area, total surface area, it's our scale factor squared. So if we have 2 squares and one is twice as big, then the area is going to be 4 times greater, because 2 squared is 4 than the original. And then if it's volume, 3-dimensional, it's going to be scale factor to the power of 3. And again, we've drawn out some of our own pretty simple examples, like 1 by 1 by 1 cube, and then a 2 by 2 by 2 cube, to kind of do a small proof of these relationships. Okay, so you can remember it, have it written down. So let's see if we can apply that to this. A large brick has 1.5 or 1.5 times the length, width, and height of the small brick. What is the ratio of the volume of the larger brick to the smaller brick? If the large and small bricks are made of the same mix of materials, what is the weight of the large brick? So this one's 3 pounds. We're going to find the volume and the weight of this, again, assuming that it's the same material that we're using. So our scale factor is 1.5, and we're looking at volume, so we're going to do scale factor cubed, or to the power of 3. So we do 1.5 times 1.5 times 1.5, which is 3.375. So that's the effect on volume. It's 3.375 times bigger, the larger one, than the smaller one. The weight, again, assuming it's this much bigger, and we were given the weight of the original, so we're going to multiply this by 3 pounds, because we know it's that many times bigger, and we get 10.125 pounds. And there's only that one practice example. We always did our and again, that rule of scale factors applies if the number is less than 1. So we can use a scale factor to make something smaller as well. And I always draw out, I know we've done this previously, but this just kind of helps illustrate. So let's say we have a scale factor of 2. So the dimensions of this are 2 times this. So let's just call this 1 by 1 by 1 cube. And this one 2 by 2 by 2. The volume of a cube is just side to the power of 3. So 1 times 1 times 1 is 1 cubic unit. Okay, this is 2 times 2 times 2, scale factor of 2. So all of these sides times 2 is where we get 1 times 2. So here's our new sides. 2 times 2 times 2 is 8. So 8 cubic units. So in its volume, this is 8 times greater than this, even though the scale factor was 2. 2 cubed, 2 times 2 times 2 is 8. So that's where we get this. So again, if you ever get confused or you're not sure, oh, is it scale factor squared, or cubed, just draw your own simple example. And then, if it's area, do a square, a 1 by 1 square, and then a 2 by 2 square. And the area of the first one is 1, because 1 times 1 is 1. The area of the second one, 2 times 2 is 4. It's 4 times greater. And that's just an easy way to kind of illustrate what we're talking about. All right, we'll do that practice set together when we get to class. All right, lesson 107, volume and surface area of compound solids. Okay, so not every shape that we have in our three-dimensional world is a perfect cone or cylinder or pyramid or cube or triangular prism or whatever. So sometimes we're going to have to break it apart into different shapes, just like we do with polygons. If we're trying to find area and different things, we can break it apart into different shapes. We can do the same thing with these. So if we have a three-dimensional shape, then we can look at this as a rectangular prism, and then a triangular prism. Obviously put those together and we have a house. And a rectangular prism, maybe a cube or another rectangular prism, and a pyramid, cylinder, and then 4 other cylinders. So again, we want to break it apart. So we have this one right here. So 24 inches up here to this door. Back here it's 30 inches. It's 30 inches deep. This is 18, 18, and the entire distance is 60. So we can use that to find what we know. It looks like we're converting all of these to feet. So 18 inches is 1.5 feet, 30 inches, 2.5 feet, just so that way it's volume. So we're going to be multiplying 3 dimensions, maybe with some really large numbers. So feet may be more appropriate for finding the volume of this. But either way, you can find cubic inches and then use 3 unit multipliers to convert it to feet, or we can convert to feet first, which might be a little bit easier, and then just calculate. So 60 inches is 5 feet, half a foot, 2 feet, 2.5, 1.5 feet. So we have all of that. So we have these 2 pillars, 1.5, 2.5, and 2. So let's multiply those. 3 together, length times width times height, since it's a rectangular prism. And we get 7.5. Okay, and then these are congruent, so they're the exact same, so 7.5. Times 2 is 15, so that's these lower sections down here. And then this one we have 5 times 0.5 times 2.5. And that's 6.25. So all we've done is rectangular prism, rectangular prism, rectangular prism. All we've done is multiply those together. So there was one of our drawer sections, and the other one was the same, so we just multiplied it by 2. And then we have the upper section, and then we add all 3 of those together, and we're adding cubic feet, cubic feet, cubic feet, so we can do that. And we get 21.25 cubic feet. All right, again, just the one example. So we'll go over these practice set problems together in class. I'll see you guys then.